we are going to take a look at some questions from the general physics section of the iGCSE physics course. So let's start off with question 1. So an engineering machine has a piston which is going up and down approximately 75 times per minute. Describe carefully how a stopwatch may be used to accurately find the time for one up and down cycle of the piston. So this is really similar to timing a pendulum or something along those lines. So what I would do is, if I was doing this practical, is first of all actually observe the motion of the piston, allow yourself to get into the rhythm of it. That will make the timing much easier. And then what you do is pick a point where you're going to start and stop the stopwatch. So I'd pick the highest position. So you start the stopwatch at the highest position. I'd measure it for about 10 or maybe even 20 complete cycles. Again, you need to make sure you stop it at the top, and then you divide by 10 to get the time for one cycle. And instead of just doing that once and saying that's the value, I'd measure it twice more and get an average time from those 3 measurements. Okay, so we've got a side view of a large tank in a marine visitor attraction, some sharks and fish and stuff. Okay. So the tank is 51 meters long, 20 meters wide. The seawater in the tank is 11 meters deep and has a density of 1030 kilograms per meter cubed. Calculate the mass of water in the tank. Okay, so first of all we can figure out what the volume is using the dimensions, and then we can use the density equation to figure out the mass. And that comes out at a very long number with lots of things, but I would round that to 2 significant figures because all the data in the question, apart from the density, is 2 significant figures. The pressure at point M halfway down the large viewing panel is 60 kilopascals more than atmospheric pressure. Calculate the depth of M below the surface of the water. So we're using the pressure with height of a fluid equation, and we want to find the depth, or H. So we've got the value of pressure, remembering to convert into pascals, and we've got the values of density and G, which gives us our height, which again I would give to 2 significant figures. Okay, so a laboratory technician has 10 pieces of plastic, all cut from the same thin sheet. The technician wishes to find the thickness of a piece of plastic as accurately as possible. Name the instrument that should be used. When we want to measure something really small, we're going to use a micrometer, sometimes called a screw gauge as well. Describe how the instrument should be used to find the thickness. So we've got 10 pieces, so that's going to be useful to us. But first of all, with a micrometer, one of the important things to check first of all is it doesn't have a 0 error, which means that when it's closed, it doesn't have a non-zero reading. And then what I'd do is I'd measure the thickness of 10 pieces of plastic, and in terms of using a micrometer, you should twist until you've clamped the 10 pieces, but not tightly clamped, because then you're actually changing the thickness of the plastic. And then once we've done that, divide the reading by 10, and that will give us the thickness of one piece of plastic. And I wouldn't be happy with just measuring it in one place. Once we've measured it in one place, measure it in a couple of other places, again give us our average thickness for a piece of plastic. So a free-fall parachutist jumps out of an aeroplane but doesn't open his parachute until after some time has elapsed. Figure 3.1 shows the graph of the speed during the fall. What is the value of acceleration of the parachutist immediately after he has jumped from the aeroplane? Well, it's going to be 10 meters per second squared. The reason being that the speed is very small, so we can ignore air resistance here. So it's just going to be the acceleration due to the weight force on the parachutist. So how can you tell that the acceleration decreases until point A? Well, it's because the gradient of the graph is decreasing, and acceleration is the gradient of the graph. And until you get to A, you can see it's decreasing all the time until it becomes constant. So state why the acceleration of the parachutist decreases until point A. Well, it's just going to be air resistance. So as speed increases, drag, as I usually call it, increases. Drag is actually proportional to speed squared. So what's going to happen is the resultant force is going to get smaller, because the resultant force is calculated using the weight force and the drag force. And if the drag force is getting bigger, weight force is constant, that means the resultant force decreases, which is why acceleration decreases. Consider section AB, so that's the horizontal section of the graph. State what is happening to the parachutist's speed in this section. Well, it's staying the same. It stays at the same value the whole time. And what can be said about the forces during this section? Well, the resultant force must be 0 if speed is constant, so weight force must be equal to drag force. At which point did the parachutist open his parachute? Well, it's going to be at B, because at that point you suddenly get the speed decreasing, or deceleration. So why is that happening? Well, when you open a parachute, the total area, or the frontal area of the parachutist, increases. That's the area actually facing and traveling through the air. And that's going to cause the drag force to increase, so that it's greater than the weight force. That means the resultant force is now upwards, so that's why they slow down. The source of solar energy is the sun. Tick the box next to those resources, which the sun is also a source of energy. Coal, yes it is, because coal is from dead plant matter, and plant gets its energy from photosynthesis with the sun. Geothermal, the source of energy, is the high temperature inside the earth, so that's not from the sun. Hydroelectric is from the sun. It essentially relies on the sun evaporating water and then it raining down on the top of mountains. Nuclear uses energy inside atoms, or the nucleus of an atom, so it's not that one. Wind also relies on the sun, because it relies on the sun heating up various sections of the earth, increasing their temperature, which causes wind to then flow in the form of a convection current. Okay, so a truck of mass 12 kilograms is rolling down a very slight incline as shown. The truck travels at constant speed. Explain why, although the truck is on an incline, it nevertheless does not accelerate. So the weight force of the truck is trying to accelerate it, so there must be a force acting against it if it's not accelerating, and that's going to be drag and friction. And they together must be equal to the force down the slope from the weight force, so the resultant force is 0. The slope of the incline is increased. As a result of this, the truck now accelerates. Explain why there is now acceleration. Okay, so the force down the slope from the weight force increases, so that it's now bigger than the resistive forces, so there's now a resultant force down the slope. So write down an equation linking resultant force on the truck and the acceleration of the truck. That's going to be F equals ma. We've got a value now for the acceleration, and we were given the mass previously, so we can calculate what the resultant force is. The frictional force up the slope was 14 newtons. By suitable lubrication, the frictional force is now almost totally removed. Calculate the new acceleration of the truck. Okay, so first of all, we have to work out what the total force was. So with the resultant force, remember we calculated as 24. We now know that the friction was 14, which meant the force down the slope must have been 38 newtons. And once we figured that out, we can put that back into F equals ma and calculate what the acceleration would be now. The lubricated truck travels down the incline, starting from rest at the top. It takes 2.5 seconds to reach the bottom. Calculate its speed as it reaches the bottom of the incline. Well, we're just going to use this equation here. So we know the initial speed is 0 because it says that it starts at rest. We just calculated the acceleration. We know the time, so that allows us to figure out the speed. The incline is reduced to the original value and the lubricated truck is placed on it. Describe the motion of the truck when it's released. So, this time it's going to accelerate, because remember we've got rid of friction acting on it, so it's going to accelerate down the slope, but the acceleration will be smaller than it was. So we just calculated it was 3.16. It's going to be smaller than that. So the diagram shows a circular metal disc of mass 200 grams, freely pivoted at its center. Masses of 100, 200, 300, 400, 500, and 600 are available, but only one of each. These may be hung with a string from any of the holes. There are 3 small holes on each side of the center, one at 4 centimeters from the pivot, and one at 8 centimeters from the pivot, and one at 12 centimeters from the pivot. The apparatus is used to show that there's no net movement of the force acting on a body when it's in equilibrium. Draw it in 2 different value masses hanging from appropriate holes. The values of the masses should be chosen so there's no net movement, and write down their values. Okay, so there are a few different options that we can pick, but essentially you need to make sure the mass times by the distance is a constant value. So this one, we've got 300 grams, 4 centimeters from the pivot. So that's going to give us 1200, a value of 1200. And we've got 12 centimeters, which again gives us 1200. So that's absolutely fine. Any other combination where you get that is fine too. Explain how you would test that your chosen masses give no net movement to the disc. So the disc should not rotate when the masses are applied, and it should remain in equilibrium. So calculate the moments about the pivot due to the 2 masses chosen. So we can plug in the values of the weight forces, which we first need to calculate. So we've got 100 grams and 300 grams, so we calculate their weight forces. Then what we do is we multiply those by the distances to give us our moments there. Okay, so then final part of this question, calculate the force on the pivot when we've got the 2 masses hanging from the disc. So we've got 3 things with a downward force, so the pivot must apply an upward force equal to that. So we've got the 2 masses that we've hung on it, plus the 200 gram of the actual bit itself, which it told us in the question earlier. So that's the total downwards force. If it's in equilibrium, then we must be an equal force upwards of 6 newtons. Okay, so a submarine descends to a depth of 70 meters below the surface of water. The density of water is 1050 kilograms per meter cubed. Atmospheric pressure is 1 times 10 to the 5. Calculate the increase in pressure as it descends from the surface to a depth of 70. So we're going to use the pressure equation that we've got here. We know density, we know G, and we know the height, so that gives us the increase in pressure due to the weight of the fluid above it. And then if we want the total pressure, we then need to add on to that atmospheric pressure too, and then that's going to give us our total pressure. On another dive, the submarine experiences a total pressure of 6.5 times 10 to the 5 pascals. A hatch on the submarine has an area of 2.5 meters squared. Calculate the force on the outside of the cover. So we're going to rearrange the pressure equation here to make force the subject, plug the numbers in, and that gives us our force acting on the outside. The submarine undergoes tests in fresh water with density of 1000 kilograms per meter cubed. Explain why the pressure on the submarine is less at the same depth. Well, freshwater density is less than salt water, so there's a smaller weight acting down on the submarine at the same depth. Okay, so we've got a track for a model car. The car has no power supply but can run down a sloping track due to its weight. Okay, so it's released at Q and it comes to rest just before it reaches S and rolls back. Describe the motion of the car after it starts rolling back until it eventually comes to rest. So what it's going to do is it's going to roll back past R towards Q, but it's not going to reach Q. And then what it will do is it will change direction, travel back through R towards S. And this process will basically repeat in loops, but each time it's going to reach a smaller and smaller maximum height until it eventually will just stop at R. So explain in terms of energy transformations why the car starting at Q cannot pass S. So at Q the car is starting with GP. At S the car has the same GP as at Q. So therefore at that point its kinetic energy must be 0 and it wouldn't be able to travel any further. In addition to that, friction and drag would do work to ensure the car actually stops before it reaches S, because some of its energy will be transferred to heat, so it won't be able to reach the same height. So a second car of mass 0.12 kilograms is released from P. It continues until it runs off the track at T. Calculate the maximum speed of the car that can have a T, assuming friction is negligible. So the change in GP from Q to T, the height change is 0.5 meters, so it loses 0.6 joules of GP, and that means it must gain 0.6 joules of kinetic energy so that total energy stays the same. Then once we've done that, we can use the kinetic energy equation, rearrange it to make speed the subject, plug the values in, and we get what the speed is. So a spring of original length 3 centimeters is extended to a total length of 5 centimeters by a force of 8 newtons. Assuming the limit of proportionality of the spring is not reached, calculate the force needed to extend it to a total length of 6 centimeters. So the first thing I'm going to do is figure out what the spring constant is using the first set of data. So we've extended it by 2 centimeters using a force of 8, so it requires 4 newtons to increase it by 1 centimeter. So to get to 6 centimeters, we're now going to extend it by 3, so 3 times 4 means we're going to need 12 newtons. So the diagram shows an arrangement for an experiment on moments. So we've got a pivot over there on the left, we've got a mass hanging on it, and we've got a spring holding it upwards. So a spring exerts a force F on the meter ruler. On the diagram, mark another quantity which must be measured to find the moment of force F. So what we're going to need is this distance here, the distance from the force to the pivot that is perpendicular to the force. So state how the moment of the force F is calculated. Moment is the product or multiplication of force and the perpendicular distance to the pivot. So the diagram shows a model car moving clockwise around a horizontal circular track. A force acts on the car to keep it moving in a circle. Draw an arrow on the diagram to show the direction of the force. Well, it's got to be directed towards the center of the circle, perpendicular to the car's motion. The speed of the car increases. State what happens to the magnitude of this force. Well, it has to get bigger. So the faster you want to travel in your circle, the bigger this force needs to be. The car travels too quickly and leaves the track at P. On the diagram, draw an arrow to show the direction of travel after it has left the track. So we're at P, and it would travel on a tangent to the circle if it leaves the track. In terms of the forces acting on the car, suggest why it left the track at P. So the centripetal force, to keep it in circular motion, is provided by frictional force between the car tyres and the road. So what this must have meant is the frictional force is too small and it can't provide the centripetal force that we need. So the car, starting from rest, completes 1 lap of the track in 10 seconds. Its motion is shown in the diagram. Describe the motion between 3 seconds and 10 seconds. We can see that the whole time it's at 25 meters per, or centimeters per second even, so it's constant speed or 0 acceleration. Use the graph to calculate the circumference of the track. So from a speed versus time graph, the distance travelled is the area underneath it. So we need to find the area of this shape. So what I've done is I've divided it up into a triangle and a rectangle, found the area of each, and then add them together. And that's going to give us our distance travelled, which is the circumference. Calculate the increase in speed per second during the time 0 to 3 seconds. Okay, so 0 to 3 seconds, we need to find the gradient of our graph. So the change in speed is 25, the time taken is 3, so our acceleration is 25 over 3, and that gives us a value of 8.3 meters per second squared. A student wishes to work out how much power she uses to lift her body when climbing a flight of stairs. Her body mass is 60 kilograms and the vertical height of the stairs is 3 meters. She takes 12 seconds to walk up the stairs. Calculate the work done in raising her body mass as she climbs the stairs. So let's first of all work out how much work she's done. So to do that, we need to multiply the force by the distance. So the force she's going to need to apply is to overcome her weight force, and the distance is the 3 meters that she walks upwards, giving us a total work done of 1800 joules. And if we want to calculate the output power, power is going to be the energy transferred divided by time. We transferred 1800, we've done it in 12 seconds, so that's 150 watts. At the top of the stairs, she has gravitational potential energy. Describe the energy transformations taking place as she walks back down the stairs and stops at the bottom. So the energy is all going to turn from gravitational potential energy to thermal energy. So the trap here is that some people are going to say it's kinetic energy, but remember she is stopped at the bottom, which means she has no kinetic energy. So all of it at the end actually must have been transferred to thermal energy and sent into the surroundings most likely. And another thing here, most people might also suggest, well, some energy as you walk, you can hear yourself walking, so isn't it transferred into sound? But in pretty much all mechanical problems, we ignore sound energy because it's so small, so it's never really a consideration in energy transfers. So name the process by which energy is released in the core of the sun. It's called nuclear fusion, where 2 hydrogen nuclei are fused to form 1 helium nucleus. Describe how energy from the sun becomes stored energy in water behind a dam. So, infrared radiation from the sun is absorbed by water, which causes it to evaporate, and it's going to go up into the sky, so it gains GPE, and it usually stops gaining GPE and at the point it forms a cloud. And then that water then falls as rain, and some of its GPE is going to be transferred into thermal energy, but some GPE will remain. So for the water that lands on the top of a mountain, it's going to still retain some GPE that we can store behind a dam and then transfer into electricity typically. So we've got some data for 2 small power stations. We've got a gas-fired power station and we've got a hydroelectric. We've got input and output powers. We are going to look at the efficiency. So first of all, what is efficiency? There's 2 ways of defining it. We can define it as the ratio of useful power output to total power input. Ratio just means divide. And we could also do it with energy as well. Useful energy output divided by total energy input. So use the data in table 2 to explain that the hydroelectric station is more efficient than the gas. So let's do the calculation. So hydroelectric, we get 30 useful out of it, we put 90 in, gives us an efficiency of 0.33. Gas, 25 over 100 gives us an efficiency of 0.25. So hydroelectric is clearly more efficient than gas. On figure 3.1, drawing a graph of extension against load for a spring which obeys Hooke's law. So Hooke's law would indicate this is a straight line graph and it hasn't started changing direction yet. State the word used to describe the energy that's stored in the spring that has been stretched or compressed. That's elastic potential energy, or it's sometimes called strain energy. So the diagram shows a model train travelling at speed v approaching a buffer. The train of mass 2.5 kilograms is stopped by compressing a spring in the buffer. After the train has stopped, the energy stored in the spring is 0.48 joules. Calculate the initial speed of the train. So I'm applying conservation of energy here and assuming we're not losing energy to the surroundings. So if the final elastic potential energy is 0.48, that must mean the initial kinetic energy was 0.48. And that being the case, we can rearrange the kinetic energy equation, plug in the kinetic energy and mass, and get our speed. In an accident, a truck goes off the road and into a ditch. Two breakdown vehicles A and B are used to pull the truck out of the ditch. Okay, and they are at an angle of 45 degrees to one another. At one point in the rescue operation, breakdown vehicle A is exerting a force of 4,000 newtons and breakdown B is exerting a force of 2,000. Using a scale of 1 centimetre equals 5 newtons, make a scale drawing to show the resultant force. So to get resultant force, we add the vectors tip to tail. So 2,000 newtons, which should be 4 centimetres long, and then 4,000 newtons, which should be 8 centimetres long, and the resultant force is going to be going from start to finish there. Use your diagram to find the magnitude and direction of the resultant force on the truck. You were essentially going to take measurements with a ruler and a protractor. So the length of it was 11.2 centimeters, so that's 5,600 newtons, and the angle I measured it to be 30 degrees to the road. So state why the resultant force is an example of a vector quantity. Well, it has both magnitude and direction. That's what vector means. Give example of a vector quantity that is not a force. There are a few. So we could have displacement, velocity, acceleration, momentum, moments even. These are all vector quantities. They have magnitude and direction. So the diagram shows a hammer being used to drive a nail into a piece of wood. The mass of the hammer head is 0.15 kilograms. The speed of the hammer head when it hits the nail is 8 meters per second. The time for contact is 0.0015 seconds. The hammer head stops after hitting the nail. Calculate the change in momentum of the hammer head. So, change in momentum, so we're going to need to know what the change in speed is and also what the mass of it is. We plug those numbers in and that gives us what the change in momentum is. Okay, so calculate or state the impulse given to the nail. So the impulse on the hammer was minus 1.2 Newton seconds, so the impulse on the nail is going to be plus 1.2 Newton seconds. Calculate the average force between the hammer and the nail. So we're going to use Newton's second law, which says force is equal to rate of change of momentum. The impulse is 1.2, the time is 0.0015, that gives us an 800 Newton force. So the diagram shows a mobile bird sculpture that's been created by an artist. We've got a pivot towards the back of the bird, and we've got some different distances measured. M is the centre of mass of the bird sculpture, including its tail, but not including the counterweight that we added later. The mass of the bird and its tail, 1.5 kilograms. The bird sculpture is placed on a pivot, so that point is going to be held fixed. The artist adds a counterweight at end E, so the tail of the bird remains stationary in the position shown. Okay, calculate the mass of the counterweight. So let's apply the principle of moment. So first of all, I'm going to figure out the moment of the weight force of the bird. So the first thing I did is calculate the weight force of the bird, then multiply it by the distance to the pivot, giving us the moment of the weight force of the bird. The moment of the counterweight must be equal to that, so it remains in equilibrium, and then we just need to then divide by the distance to give us what the weight force must be, and then finally divide that by 10 to give us what the mass must be. The centre of mass of the sculpture with counterweight is at the pivot. Calculate the upward force acting at the pivot. So we've got two downward forces, 6 newtons and 15 newtons, giving us a total downward force of 21 newtons, so the total force upwards must be 21 newtons as well. So the sculpture is rotated clockwise to the position shown in figure 2.2. It is held still, then carefully released. Okay. State whether the sculpture will stay in that position, rotate further clockwise, or rotate back anti-clockwise. So it's going to stay in exactly the position it's in. So why is that? Well, the distances to the pivot for both the mass of the bird and the counterweight will decrease by the same factor. So they'll both be, say, I don't know, divided by a number, maybe 2 or whatever it is. So because of that, their moments are still going to be equal. Or another way of phrasing that is the center of mass of the whole object is still going to be at the pivot point. And all of that means it's still going to be equilibrium, so it would not rotate. The rocket shown in figure 2.1 is about to be launched. The total mass of the rocket and its full load is 2.8 times 10 to the 6. The constant force is provided by the rocket's motors is 3.2 times 10 to the 7. Okay. Calculate the total weight of the rocket and the fuel. We just need to multiply the mass by 10. The resultant force acting on the rocket, so that will be the thrust minus the weight force, and that gives us a value of 4 times 10 to the 6 newtons. The acceleration, we can just use F equals ma. To calculate what the acceleration is, plug our value for the resultant force in there, and that gives us our acceleration. Suggest why the acceleration of the rocket increases as it rises above the Earth's surface. Well, I think there are 2 reasons here that we could use. The weight acting on the rocket decreases as its fuel is burned. And the other thing is drag from air resistance will decrease. The atmosphere gets thinner the higher up you get, so drag is going to decrease as you go upwards. Another one that we could add that's not really part of the specification but is definitely true is the further away from Earth you get, the smaller the weight force acting on you from the Earth will be. So that could be a valid point because rockets are going into space, so their distance from the Earth does increase significantly. Okay, so wind turbine has blades which sweep out an area of diameter 25 meters. The wind is blowing directly towards the wind turbine at a speed of 12 meters per second. At this wind speed, 7,500 kilograms of air passes through every second through the area. Calculate the kinetic energy of air traveling at 12 meters per second passing through the circular area in 1 second. So, then to get the kinetic energy per second, we'll multiply the mass per second by the speed. That gives us 5.4 times 10 to the 5 joules. The turbine converts 10% of the kinetic energy to electrical energy. Calculate the electrical power output. So, we know the energy is going to be 10% of that kinetic energy, so 5.4 times 10 to the 4. And power is energy divided by time, but this amount of energy is the amount of energy in a second. So we've actually already calculated what the power of it is in watts. On another day, the wind speed is half that in A. Calculate the mass of air passing through the circuit area per second on this day. So if it's going through half the speed, that's going to mean half the mass is going through, because the area it's passing through is the same, but half the speed would mean half the mass. Calculate the power output of the wind turbine on the second day as a fraction of that on the first day. So, if you times the speed by a half, kinetic energy is going to be times by a quarter, because remember kinetic energy is proportional to speed squared. So halving speed quarters kinetic energy. But we've also halved the mass, which is going to halve the kinetic energy. So overall, the kinetic energy per second is going to be divided by 8, and therefore the power is going to be divided by 8, which will be 6,750 watts. So final question here. So the diagram shows apparatus for investigating moments of forces. So the uniform meter ruler shown in figure 2.1 is in equilibrium. Write down 2 conditions for the meter ruler to be in equilibrium. Okay, so the first thing, we need the resultant force to be 0, or the forces to be balanced. And we need the resultant moment about the pivot to be 0. So the moment clockwise equals the moment anti-clockwise. Okay, so we want to show the value of the reading on the spring balance is 8 newtons. So we can apply moment clockwise equals moment anti-clockwise. So we multiply each of the forces by their distance to the pivot. Then we can rearrange to find what the force is, and we can see that it does indeed come out as 8 newtons. The weight of a uniform meter ruler is 1.5 newtons. Calculate the force exerted by the pivot on the meter ruler. So, the resultant force of the 3 forces we know about so far, well, we've got 6 going down, we've got 1.5 going down, and we have 8 going up. So the resultant force without the pivot force is upwards 0.5. So what that means is the pivot force must be 0.5 newtons downwards, so the resultant force is 0 and it's held in equilibrium. And that completes this video reviewing the questions on general physics.